pleasure to finally have Ian here. I've been after him to come up from UC Davis and give a talk. I've known Ian for, I don't know how long, at least 10 years.
18 years or something?
18, something like
John
that.
Lunshaw introduced us at NENCAR.
Yeah, we worked together a long time ago. So Ian is an associate professor at the University of California, Davis. He studied physical chemistry at UC Santa Cruz, including summer research in computational chemistry at Los Alamos National Lab. And then he earned his PhD in meteorology at Penn State University. For 4 years in between, he worked as an air quality consultant for Secor Incorporated in Fort Collins, Colorado. Later, he went to NCAR, the National Center for Atmospheric Research, and he did a postdoc appointment there. Postdoc is when you finish your PhD, you do 2 years of research under the direction of someone else before you go off and get a permanent job. So he did that before he went to UC Davis and joined the atmospheric science faculty there. His research interests include the airborne observation of vertical mixing and near-field pollutant dispersion, observational emission estimates, the meteorology of coastal fog, planetary boundary layer dynamics, biogeochemical cycling, and atmosphere-ocean photochemistry. It's a man of multiple talents.
A lesson in padding your resume. Okay. Thank you, Shane. Great to see you here in person. Lovely campus. Really glad to be here. Sorry, I just kind of rolled into town. I'm sweaty and road haggard. And unfortunately, I packed a whopper. So hopefully you guys are good until about 6 or 7. Because I've been working on this scientific problem for, I would say 5, maybe, no, 6 years. And what they don't tell you in graduate school is that when you pose a scientific question, you go to answer it, it's a lot more than, the better part of a decade goes by before you have anything substantial. So it's a multi-component argument I'm going to make, and we'll just try to get through as many as we can. We'll see what happens. You're going to hopefully learn something. Yeah, let's get the front lights on.
Yeah, perfect.
So I know this is a kind of a broad department here, so I wanted to start, for those of you who might not be as familiar with atmospheric dynamics, with a little bit of a quick lesson and then a history lesson, and then we'll get into it. But as you may know, this is the net radiation. Atmospheric scientists are obsessed with this because this is the it's the incoming solar that's not reflected away minus the outgoing infrared radiation, and this is the net averaged over the year across the globe. You see positive inputs numbers here in the tropics, negative numbers here, so it's radiatively cooling in the poles and radiatively heating from the sun in the tropics, which creates this temperature gradient across the globe, which drives the whole shebang, the engine of the atmosphere. Is driven by this. So one of the consequences of that is you get a jet stream in the mid-latitudes, sort of classic cartoon picture. You hear about it a lot in the weather reports, so you're probably familiar with the jet stream. It's up high, and it's basically an integrated consequence of this of the strongest temperature gradient in the horizontal that actually impacts the winds aloft. So you typically see like cartoons of jet stream and it wiggles around, and there's another jet stream called the subtropical jet, which is not always independent, slightly different physics, and anyways, we won't get into all that, but there's this jet stream. You know it from probably flying in the mid-latitudes, this strong current of air. Oops, yeah, that's not even good. Okay, but what you might not know is that typically in your classic atmospheric science text, you're going to find some statement about how World War II bombers, of course, the victors, tell the history, right? They write the history. So it's like the Allied bombers were flying, and they realized that sometimes they get these hellacious headwinds or tailwinds when they were going up high at the top of the troposphere. So you'll find quotes like this often describing how we discovered the jet stream. But it turns out, when you look into it, this John Lewis, actually from University of Nevada, Reno, wrote this incredibly fascinating article a few years back exploring its history. It turns out the Japanese discovered it in the 20s. And that was pioneered, right? They didn't write the history, but it's really interesting how it didn't get in the history books, so I'm going to tell you about that. Oishi was the scientist. At the time, in the 20s, Japan was heavily industrializing, trying to become more like a Western power, and trying to create a world-class science institution. So they were working like crazy, and he established this observatory outside of Tokyo and was launching these balloons, and with a theodolite would track how they move with height and time and measure the winds as the balloon lofted up to the top of the troposphere. So this, you probably can't see these numbers exactly, but this goes up to 10 kilometers. This is wind speed in kilometers per hour. Publication from the 20s of his. And you can see, I love this because what he decided to do was put it into an Esperanto journal. Because at the time, this was going to be the universal language that everyone in the world was going to speak. And so you can see these great words in here that you can sort of recognize, like vintro, this is winter, autumno, printempo. And so you see that in the wintertime, there's these really impressive wind speeds that were measured at this observatory aloft, approximately 10 kilometers high. So it comes out in an Esperanto journal, no one reads it. But the Japanese knew about it. So one of the things they did with it was they weaponized it in World War II and actually developed these big balloon payloads, so hydrogen balloons, that they would load up with bombs, incendiary materials, and they had this elaborate kind of, they had ballast that would drop if it got too low, and it would let out some hydrogen if it got too high. And it did this amazing mechanical instrument that went up and rode that jet stream over. And the idea was they were going to just set the Western North America ablaze. And so everyone would be busy putting out the fires, and they wouldn't be able to attack across the ocean. And so this is a map of the sites where they were actually found. There's one fascinating story about one family that actually did find them on a picnic, and it actually blew up, killed 4 or 5 people. It was the only civilian North American casualties from the war. Just a fascinating piece of history. But they were aware of this jet stream long before we were, and tried to use it. So there's this giant current of air aloft. But of course, does anyone notice what the problem might be? If you're trying to burn the forests of the West, it's easy to do now, right? You see it. But these winds are strongest when? Vintro. Right? When the forests aren't that combustible. So it didn't quite work, but it was a brilliant idea. But I just wanted to introduce this history as sort of a lead into how we've gradually come to understand the atmosphere as being much more interconnected than we traditionally thought. Like if you were an air pollution scientist in the 50s or 60s, you would think like pollution is your neighborhood problem, right? Or the old dilution is the solution to pollution. You put the stack up a little bit higher and it's someone else's problem, but it's a nearby thing, right? And gradually, with nuclear fallout being a big concern, because we were detonating, post-war, we were detonating these thermonuclear bombs all over the world, above ground, and so the dispersal of all that effluent was a big concern, which really helped establish the field of atmospheric chemistry. This guy, Christian Junge, is sort of considered the godfather of atmospheric chemistry. Wrote this sort of groundbreaking book in the early 60s, kind of establishing this new field. It was a new field of chemistry and atmospheric dynamics. Junge himself was trained as a meteorologist. So he was busy writing these, I don't know if any of you have taken these classes where you have to write, make isobars from the data, and you're isoplepping on maps, and you get weather maps together. And he had all this experience with that. And some say that's one of the ways he eventually started measuring particles in the atmosphere. And those were discrete measurements at different sizes. And Junge would actually connect them with smooth curves because of his training as an atmospheric scientist. So anyways, I find it funny that chemistry, atmospheric chemistry, and meteorology have really are very, very disparate fields in a lot of ways. People are trained quite differently in those fields. yet the father of chemistry was really trained as a meteorologist. So that's just one of my little quick soapbox things here. But gradually, as the 60s go on, people discover little particles in Barbados coming from the Saharan desert. They realize it's an important source of iron, nutrient-limited micronutrient in the Sargasso Sea in the Caribbean, and they start making these connections. Glenn Shaw starts seeing these desert events in Mauna Loa in Hawaii, and I also want to point out this will be my last historical thing. I think this Claire Patterson, some of you geologists may know this person's name, but everyone should know his name. He's sort of like the most famous scientist never to win a Nobel Prize and to be basically unknown. But first he did was using lead isotopes, he was able to age the Earth. You know, boom, like right out of grad school, mid-50s, he says, the Earth is, how old is the Earth?
6.
The number came from him in the 50s. It's changed by a few percent since then, but he nailed it, right? Nailed it. And he did it with these really detailed, scrupulous measurement techniques that needed to be very, all clean rooms, all that kind of technology derives from his work. But what he found in the process of trying to date the Earth is that there was just lead dust everywhere. He had to use meteorites to date the Earth, or the solar system, because there was so much lead lying around everywhere he went when he went to take samples. He'd go to Hawaii, go to oceans, Arctic, and there was just a ton of lead. So his research then, after that, became an environmental science story where he pioneered the establishment of the Clean Air Act, the Clean Air Act amendments, not the amendments, the initial one in the late 60s when the EPA was just beginning, and it came under all kinds of industry attack because the people who were the experts in lead science were all funded by Standard Oil and their subsidiaries. So it's a fascinating history of the struggle of environmental science in this one mild-mannered Midwestern kid named Claire Patterson, which I've grown quite fond of, but he used lead. That was his tool of choice, and he looked at isotopes of lead, and he even looked at this issue of how you go to the tropics in the middle of the Pacific on a little atoll, and you'll find a bunch of industrial lead from Japan, and you can fingerprint that. And I'm going to talk about this technique that I used, a similar technique, with colleagues at Lawrence Berkeley to do something similar. All right. So anyways, it's kind of been this progression that everything is sort of linked, and then ultimately, right, with the greenhouse gas saga, people realize, oh yeah, well for CO2, if you emit CO2, that's not going away anytime soon. So then it becomes a global problem. It's not a local pollution issue. So greenhouse gas and climate change studies really kind of cemented this idea that the whole shebang is connected. Okay, so enter NOAA, the National Oceanic and Atmospheric Administration, and Dave Parrish in particular, who in the early 90s, there was lots of these ideas going around and stuff was transported all the way. Early 90s. So, this is the kind of thing that won't work on this computer. Doesn't matter. Early 90s, they do an experiment in Sea Ranch, if you know that area north of Bodega Bay, along the coast, and they try to measure how much of the junk in the air is coming from Asia, and it's really complicated because when you're looking at air at the beach, I've done this a fair bit, it looks like ocean air. And so the signal of something coming from very far away is very muted. But, so Dave Parrish, after doing that and saying, yeah, we think there's transport of Asian stuff like everyone else kind of thinks, blah, blah, blah. That was in the early 90s they did that experiment. Then in 2010, he writes this paper that he came to Davis. I remember talking about it before it was published, and I thought, this is a fascinating idea, and it really kickstarted a bunch of research that I'm going to try to talk about today. So he took these, Trinidad Head is not far from Eureka on the coast, where NOAA operates sort of a climate monitoring station. And they've been launching balloons that measure ozone as you go up with the balloon for 15, 20 years. once every 2 weeks, and he started looking at this mass data set, and what he noticed was there's a correlation with the ozone aloft, so these are profiles of ozone, but now correlated with the surface sites across your neighborhood. So in the northern Sacramento Valley, and then some of the mountains up here in Shasta and Lassen. So he looked at those surface monitoring sites and showed that there was a correlation with these ozone measurements at the coast, but it was only up at elevations of 1 to 2 kilometers where they correlated well. So his hypothesis is that this is loft, this is Asian or trans-Pacific pollution that's coming in and eventually mixing down over the rough surfaces of the mountains and valleys and influencing the ozone on the ground, which has been, you know, again, the Clean Air Acts were established in the late 60s, I think, maybe early 70s, eventually when it came into law. But basically the way the government deals with it is it's like a speeding ticket. It's like if you have more than this amount of ozone in your air, I'm going to give you a ticket. Turns out you don't really have to pay it. I mean, it's a little bit more loosey-goosey, but it's a problem. So, but they do it just with this threshold. And so this threshold becomes what everyone's gearing, you know, shooting for. And so if you start to accept this idea that there's this long-range pollution that's coming in from sources that we have no control over, well, of course we buy all their products. and trader agreements allow them to basically treat the environment any way they want, then it basically comes back and influences us in a way that we can't control from our local emissions, right? It's amazing how long it takes people to learn this, all of us. So, okay, so just to give you that was Dave Parrish's paper from the northern Sacramento Valley. All the work I've been doing is in the San Joaquin Valley. So you're just gonna have to shift, you're just gonna have to drop latitudinally for a minute and bear with me. It's very symmetric, very similar, right? The Sacramento Valley, San Joaquin Valley, so it's comparable. So I'm going to be looking mostly around sort of Fresno, down to Bakersfield area, but the same idea applies. There could be air coming in from offshore over the coastal mountains and then mixing down and influencing pollution. So if you look at, this is from the California Air Resources Board, these is number of violations, I believe, in the San Joaquin Valley, and you have, you know, there's improvement going on, so that's a good sign because of all the regulatory influence for all these years, trying to clean up emissions, trying to clean up auto emissions and VOCs and all these things that go into making ozone. But this is what it looks like. I think I have preserved the axis for example, the South Coast, LA, the one that's really famous for its air pollution, and you see dramatic improvements. So gradually through this period, which is something like, what, 30 years? 86, well, it's, yeah, 30 years, 86 to 2016, gradually LA started looking like it's even cleaner than the San Joaquin Valley, and the question arose, why is the San Joaquin Valley so resistant to cleaning up its air? And that's where I got involved with this idea that perhaps it is, you know, how much of it has to do with this long-range transport of pollution. So these are not going to come up well, but it's okay for the most part. The bottom line is you don't really need to understand this curve exactly, but the point is that global measurements of ozone indicate that in Europe and most of the high altitude North American sites, sort of away from big cities, that sort of what we think of as the background atmosphere, has an ozone trend that's been going up, and this is around 2000, this dashed line here. It's been going up, and it looks like it's curling over. For the last 10, 15 years, the background, not an urban problem, but a background atmosphere seems to be decreasing in ozone. But if you look at similar data in mountains in Japan, or in the marine boundary layer along California, and other places, these high altitude places, this is again, this dashed line is 2000, forgive me, you see that there's this general trend that hasn't really curled over. Whereas North America and other parts of the world that have been cleaning their air, it looks like it's curling over, but it looks like the effluent from Asia still hasn't quite rolled over. And that's consistent more or less with what people estimate to be the emissions from Asia, although that's not a very precise science at this point. So the point is that there seems to be this trend. It's not global, it's specific to the Pacific. I never and that one. And it could be, as this goes up, right? If you think about it, if this background air that's flowing into California goes up, and it turns out that every, I'd say 10, 15 years, the EPA says, you know what, we've learned the ozone's not really, it's more harmful than we thought, so we're going to ratchet down that speed limit. So they've been doing that as National Ambient Air Quality Standard, the official standard. They've been ratcheting down every so often as they learn more about deleterious effects. And so the question becomes, well, if the background is going up and we keep legislating it's got to be lower, you know, where is that going to collide and how much do we have in our own power to control that? So just a recent study by satellite, also you can look at this stuff by satellite. These are images of ozone from space, averaged over 2 years or so, or a year plus. And the red colors are high ozone, and light blue is low ozone. And this is the sort of across the Pacific. And you can see from 2005, 2006, it may look like this in the long-term average. And 2009, 2010, it looks like, oh, a little bit brighter. Yes?
Do you want to draw a distinction between stratospheric ozone and perhaps...
Oh yeah, this satellite specifically looks at the ozone in the lower part, right? So that's a good point. Originally, you learned about ozone probably in terms of its presence as a helpful UV spectral filter in the stratosphere. Well, it has a lot of impacts in the stratosphere, but the point is ozone there was an ozone hole. You've heard of that environmental problem from a few years back. And that had to do with the ozone, which 90% of it is up in the stratosphere, where basically you never have to breathe. Approximately 10% on average globally is down here. And when we emit things like nitrogen oxides and VOCs from cars or from gasoline vapors, these different things react in the atmosphere down low, and they create ozone at much higher levels than is sort of natural in the background. So yeah, there is this distinction. We call it near-surface ozone as being harmful. It reduces crop productivity, for example. It has impacts on pulmonary health and more that we're learning about, but it's a different issue. So there's natural ozone, it's way up high, some of it mixes down, so ozone is natural, but there's a point where it gets too high and it becomes quite harmful. So yeah, there's this distinction, and satellite scientists for a long time have been able to actually distinguish the two. So this is actually ozone only in that lower bit that we care about where all the weather is, the troposphere, that lower sort of approximately 10 kilometers, where the jet is at the top of. All right, so you see that over time, that it looks like there seems to be more ozone, and it seems like this kind of gives you an indication that it looks like it's coming from over here. This is then satellites. You can also look at NO2, nitrogen dioxide, was one of the key ingredients to making ozone. And so this study made this argument that here, it's a little less visible, but 2005, 2006, it looked like this. 2009, 2010, 5 years later, it looked like, or 3 or 4 years later, it looked a little bit brighter. So again, it's consistent with the idea that Asia is definitely putting out more, is still on the upswing in terms of its emissions for precursors for this harmful ozone down in the troposphere. Okay. So anyways, it's been on people's mind for a long time. If you look, I guess that's not going to show. I'll just show you this one. This is from a paper, fairly old now, but they're trying to model it. So there's people making measurements up in Oregon at a ski resort, Mount Bachelor, and the measurements are these black dash line obs. And this is just like a 1 month. And this is the speed limit, that red line. And so the observations show that even up there, high, it's something at like 2.5 kilometers, I think, this mountain site, the air can actually violate this standard because it's getting air from far away that has these high concentrations. And these colored lines are just various people's attempt at putting it all on a computer and then flipping the switch, taking a nap, and then seeing what the computer spits out, right? I'm sure it's more detailed than that. But they, this is kind of the constant battle of like trying to get your models to really reflect reality. And whenever I look at these things, I see, because I'm a biased observationalist, I see like a low-pass filter after a few beers. Like it generally gets the shape right, like, okay, I should be going down now, all right, maybe I'll go up down here. But it's a little bit sluggish, it doesn't quite do it, doesn't have these sharp edges. This is, in my opinion, this is really the essence even of climate modeling. I mean, it's like, basically your numerical model cannot contain everything, right? It's just too complicated to track everything. So it loses a lot of its richness, a lot of its spikiness, a lot of its variability, and computer models are constantly trying to improve that. So the point is that we don't really have a good sort of a priori understanding of where this ozone's coming from because we can't really simulate it that well. Okay, so enter my efforts over the last, like I said, very long time. What we decided is that because of the lessons learned in terms of looking at the air at the beach, hard to see the signal. But if you get up high, there's all these coastal mountains in California where if you get up high, like if you've ever been to Big Sur and you look up and it's like cold and foggy and windy, and then you just go up a few hundred meters into those mountains and it's like bone dry, hot and dry, and there's oak, shrublands. And so we thought if you could get up here into these mountains, you can get away from that influence of the ocean and see air that has been traveling and not contacted the surface for quite some time. So we did this one in Mendocino. This is an old fire lookout tower that is not operational right now, and one in Choose Ridge, which is above Big Sur, up from the Carmel Valley, where there's this team of rogue astronomers who built this off-the-grid observatory. It's so cool, all on their own. And they got a wind turbine and a bunch of PVs, and they allowed us to actually build a little climate monitoring station in there with them. And they're very, very scrappy, very resourceful folks. It's been a lot of fun. So this is about 1.5 kilometers, and the idea is the airflow up there is blowing onshore, and so we're able to look at air that has this sort of long history over the Pacific, but not usually mixing it up with the surface of the Pacific. And I should mention the ozone problem, air pollution problem in the San Joaquin Valley. San Joaquin Valley has other problems, but the ozone problem is a summertime issue because this production that happens with these nitrogen oxides and VOCs, they require sunlight and a little bit of higher temperatures, and so that it's a summertime problem, the ozone is. The particulate matter, which is also a problem, tends to be more of a problem in the winter, so it's a separate kind of issue. So if you are used to looking at weather maps, we often show things in terms of like pressure. We'll just call these pressure isobars, pressure surfaces, and you read them like terrain maps, like topo maps, and you see that here is high pressure, here is higher pressure, lower pressure, higher pressure, and this we then call a trough. So it looks like a little depression in a surface. And when we teach this in basic meteorology, we say that if you don't have too much complicating things happening, like a severe storm going on, or severe topography like the Sierras, that generally the flow is parallel to these lines, parallel to the isobars. That's one of the things you learn. And I just show this that if you go up high enough, you tend to have what I was saying, right? This is where Choose Ridge is. So the winds that's following these lines basically winds up blowing onshore from the southwest. And that's what we see when we're at Choose Ridge, but only 2/3 of the time. 1/3 of the time, you have flow that's actually blowing from the north-northeast, basically from San Jose, and it looks like California polluted air. And the reason that is there's this tug and play between the general background flow and, I won't get into it, but the heating of the interior of the southwestern U.S. creates this what we call thermal low, and it distorts the pressure field that drives flow offshore or northerly flow sometimes, if it's hot enough. So we have to be careful in filtering our data and only look at times when the flow is coming onshore, because about 1/3 of the time we see junk from the continent. Okay, this work that I started at this Choose Ridge site in above Big Sur, eventually led to this project by the California Air Resources Board sponsored called CAPITS, because everyone loves a good acronym. California Baseline Ozone Transport Study, which took place in 2016 and we were part of, and we were doing flights between Fresno and Visalia in this blue box, and we would spend all day flying back and forth in 105-degree weather and the turbulence at the boundary layer. We earned that data. Many sick bags full. I've taken a lot of students up, and there's a lot of liquid record of those trips. We should keep it in the cabinet in the back. Oh yeah, I remember Teresa. Anyway, no, well, we earned it. It's good. If you feel like, people who collect their own data are kind of twice warmed. Like that old adage about the chopping your own wood. So, anyways, but in the meantime, NOAA, the National Oceanic Atmospheric Administration, has their ozone LiDAR. Oh yeah, Shane's got a LiDAR, right? So it's a similar technique. Hopefully you've heard of it, you've seen it, but it actually specifically looks for ozone. And it measures ozone concentrations as a function of height, and they parked it in Visalia. There's also a radioacoustic sounding system, so you can get temperatures and winds with height from this site, and we did the flying around to sort of integrate that measurement. We had measurements at the coast mountain site, and then San Jose State, researcher Sin Chow from San Jose State, and his team had these ozone sondes they were launching now daily. As the NOAA data set is once every 2 weeks. They were interested, California was interested, well, how much does that change day to day? And so they launched these balloons 6 days a week from Bodega Bay and Half Moon Bay to kind of try to capture what's coming on shore and how is that affecting the ozone down here. And so the colored lines I just put in here to show you that aloft, the flow I was talking about over Choose Ridge flows over the coast range and over the valley, but the flow down low under the Pacific High is kind of pushing up against the coastal mountains. It comes from northwest, and it's basically kind of trying to get onshore. It's pushing up, but the mountains tend to block it. So it's pushing, blowing. As you know, summertime along the coast can be quite cold and foggy and windy. And when that fog and wind reaches anywhere where there's a gap in the mountains, Petaluma's a good one, or the Golden Gate's the classic one, it breaks in. And so the feedstock for the air in both your valley and the San Joaquin Valley, more or less down low, come from this feed from the marine layer coming in through the breaks in Petaluma and the Golden Gate Ridge. Well, Golden Gate. Okay, so that's the general layout, and I'm going to be talking about these sites in a little bit. Okay, but first to focus for a second on our data from Choose Ridge, which we've been measuring now for 5 years. I just wanted to show, well, we don't really need to look at all this, but if you go up there and you measure ozone, this is an average ozone during the summer ozone season, June, July, August, September. And this is every hour of the day, and these are standard deviations plus or minus, but this is a long-term average, at least 3 years in this data set. And you see that overnight the ozone is, somewhere averages around 50 parts per billion, and then in the daytime it actually goes down, which is the good sign that you're measuring background air that's clean. It doesn't have the precursors necessary for the sunlight to make ozone. If you look at these, this red line is from Fresno, green line is from Arvin, which is south of Bakersfield, deep in the heart of the valley, at actually the cul-de-sac of the valley, right at the end. And then this golden line is actually Lower Coeta, which is about 1.8 kilometers, but on the downwind side of the San Joaquin Valley. And what you see is that this mountainside, while at night it looks similar to the mountains upwind, in the daytime it still has this bulge. This bulge is all the junk from the San Joaquin Valley blowing up the hills and creating ozone, and you can see it in just the average behavior of the ozone. But down low, at the valley floor, you see this tremendous growth, rapid production throughout the day. So the question becomes, well, how much of this production here is due to things that we can control? And this has been studied for decades and decades. All right. So you can make pollution roses for fun, where you look at sort of a histogram of the concentrations of ozone over these 3 years as a function of wind direction. Remember I told you that 2/3 of the time the winds are coming from the southwest or west, and then there's some time where the wind's blowing from the northeast, and you can see these colors give you the bins of the amount of ozone in each. And what can you see? You can see that the average ozone from the northeast, when it's blowing from the interior of California, is orangish green, 60 say parts per billion, which is higher than the average, right? The mean of this. But look at the highest ozone values you see, these dark reds and browns, are occurring when the wind is blowing onshore. So the highest ozone we observe there is coming from somewhere else, and then it's eventually blowing over. I'll try to give you a visual of this. That's the northeast over the Central Valley. That's looking west to this is the coastal mountains, and that basically you can see maybe the fog layer of the ocean right beyond. It's about 20 kilometers upwind. It's the coast. Okay, so another thing we tried to do was measure particles in this instrument that was developed at Davis decades ago, and it's an impactor. So it pulls air in, and then it has these little mylar films that are about this long, and they're wrapped around a drum, an aluminum drum. And there's 8 of these drums. And the air comes in, and based on the aerodynamics of the air flowing through, there's actually a little bit of film. They put a little goo, like lab grease on the film, on the mylar film. The air comes in, and the big enough particles with enough inertia smack into the goo and stick there. And then it goes on to the next one with the different aerodynamics, and it smacks in some more. And what it does is it segregates the size of the particles based on the flows through these 8 barrels, around these 8 barrels. So you get this size-segregated collection of aerosols that are stuck onto this film, and then every 3 hours, the barrel goes just a little bit. And so over 6 weeks, this thing will operate for 6 weeks unattended. You come back after 6 weeks, swap out the cartridges, take them back, and you have this, like, whatever, 6 centimeter long, basically, ice core, right? It's this 6 weeks history of what the particles look like coming in the winds at this mountain site. Then we take it down to the advanced light source at Lawrence Berkeley, and you can do pixie analysis. You can do, this is actually XRF, X-ray fluorescence. So you hit it with this high energy light, and based on what kind of colors come off of it in response, you can tell the elements. The point is you then get this huge data set. You have every 3 hours, that's about the time distinction, you get a measure of the different sizes and all the composition of those. Well, not all of them. It's only metals beyond about iron that you can measure with this. So it's heavier elements that you can see, but there's a lot of information. So you put all this information in sort of a statistical, package which kind of sorts them out into basic tendencies. And it's kind of a qualitative hand-wavy thing, but basically it says, okay, this stuff has all the characteristics that look like, this might have come from the ocean. So this might look like it comes from combustion locally, or this might look like it comes from dust. It's got sort of crustal characters. And so we do this for about 4 different characteristics, and sure enough, 2 of them look like Asian. One looks like Asian dust, and one looks like Asian combustion because of all the sulfur in it, the sulfate from dirty coal burning. And so you can make pretty pictures like this, which give you sort of this distribution, and sort of this. It's a much more sort of a fun visual pattern recognition kind of science, right? Not firmly rigorous, but it's good enough to get some of the job done. So, but we ran into this guy, John Christensen at Lawrence Berkeley, who said, "Hey, I can help you with this. I can do lead isotopes like no one else." It's true. And so he does these 4 different, is it 4 or 3? 206, 207, 208 isotopes of lead, and looks at their ratios, and he sampled from all over the world, and it turns out, and this is like I'm saying, Patterson started this whole process back in the 60s, turns out you can delineate from the ratios of the lead. This is stuff that comes from China. So the crustal material in China has a different isotopic signature than dust from the North American plate. And this has to do with the thorium-uranium ratio in it for some reason that I don't completely understand. But the point is there's separation. North American data looks like this. Oh, sorry, this is Chinese, sorry. This is Chinese data that was collected in China from the soil. And then these are all these different data points, some of which are just purely North American. And so we start segregating by how far they are separated in this isotope space to give us a sense of what fraction of the lead is Asian origin or what fraction is North American. You can actually quantitatively say something about this mixed sample you're collecting on this mountain. And so the fun part about this, well, and I should say that he published something which you can't see here, but basically he did a few samples here and there all throughout sort of the Central Valley and the coastal mountains, and he's got all this different data, but if you just look very roughly, on average it might be 40% of the lead he found was Asian in California. So we took those little aerosol records that we kept, fortunately, we did the analysis but kept them, and we selected a few times where we thought this would be interesting to see what this looks like with the lead, and we gave the analysis, we gave the samples to him, rinsed them off, he did the lead isotope samples, and by this kind of touchy-feely factoring method where we kind of group things and say, this looks like Asian dust, this looks like Asian combustion, and you look at the actual quantitative lead isotope measurement, which is here on this axis, and these are all the data that we brought to him with our kind of loosey-goosey analysis, and sure enough, they correlate really well. So we thought, that's great. This is actual confirmation that this method of grouping looks like it does capture the Asian influence, or the Asian character of the aerosols quite well. Okay, so now, this is just a handful of points, but the analysis we did with the 8 drums with all the different aerosol sizes and their elemental compositions, we then did the analysis there and looked at a whole year, and we were able to see interesting patterns. So we say, well, what is that? The stuff that looks like it's coming from Asia, what's the ozone look like in that air? So not particles, but the ozone that we were also measuring up there. And I'll skip that. And sure enough, our factors, so this is our Asian dust factor. Again, it's noisy, but we see a trend that looks like the more Asian dust we see, the higher ozone we see. So, it's not that groundbreaking, but we were really excited to see this because now we have a quantitative, statistical way we can represent the influence of the Asian air mass and how much ozone that is above the standard ozone, the typical ozone. So this has been detrended here, so you don't get seasonal effects of the ozone going up and down. And likewise for our Asian combustion, we also have a sloped line. So now we say, okay, if these are the 2 main components of Asian influence, we add these together and we can say, on average, because of the way this factoring is done, the average is just 1 throughout the whole summer season. You average these things and you get 1. Now I can quantitatively say, oh, with 1, the average effect on ozone is X amount. That turns out to be this slope. So if you add these two, you get something like 4 parts per billion of ozone on average. It's always fluctuating, but on average, that's coming from an Asian source, we think. So then we looked at the ozone data from the mountain site, and ARB was doing independently, before the whole CAVITS project, was doing these profiles, and we took all this ozone data and we looked at a correlation of the ozone at Choose Ridge, which is about 1.5 kilometers here, and then the ozone measured by these airplane profiles that ARB was doing in Fresno, and we found that it tended to correlate most right down here, down low, near 1,000 meters, which happens to be right above the boundary layer in the valley. Okay, so this is different lags, not as important, but the point is the measurement at the coast seems to be tracking the air actually over Fresno to some degree. So this is a cartoon image of what this flow looks like with a cross-section sliced across the valley. So this is the valley axis coming out of the board here. And this is an actual terrain data that we took and binned into about a 5 kilometer wide swath. And so this is the coastal This is the Coast Range with the northwesterly flow in that shallow marine boundary layer, that marine layer. This is the Choose Ridge site. This is Salinas Valley. This then is the San Joaquin Valley. And these are the big Sierras. So this flow then, like I said, the feedstock's coming in from the Golden Gate, more or less, and then coming up the valley this way towards us. But there's also this air aloft that's flowing in towards the Sierras, and it may or may not have, I try to make this tongue-looking thing of ozone, these broad lamina of ozone that are flowing on shore. And what happens is the wind that's flowing up here basically piles into the Sierras and has to stop. And when it stops, it turns out it weakens the Coriolis force, which is pulling it to the right, and it flows down the pressure gradient, which is that trough I showed you earlier. So it tends to flow into the board. That's why I do this little vector sign of the flow going into the board. But if you go further south enough, some of it's flowing around the Sierras to the south, where they're not as high. The southern Sierra are very, very high in general. So this flow comes in here and it stagnates, and then the boundary layer in the valley's just kind of doing its thing, which is always mixing, but it's mixing air that's not from the background atmosphere. It's mixing the semi-polluted air that's been contaminated by its presence in the valley for so long because it stagnates aloft. Okay, I guess we should probably finish this up, huh? Okay, so this enter our, we've been doing a lot of airborne research. This is the team, and the company that actually owns and operates the planes is called Scientific Aviation. They now have 3 planes in their fleet. One of them's in Lincoln, north of Sacramento. 2 are in Boulder now. This is an old picture, but this is the kind of thing that we spend time measuring. Let's see, I already explained that, so I'm not going to tell you that anymore. So I have to figure out how to do this, because we should probably end, right?
You're good.
Yeah, you got time.
Okay, so then this is what I was saying. This is a multi-piece argument that I'm trying to make.
Not an hour, but you got time.
Not an hour?
No.
Okay, I just want to make some of these points. So, well, that's all right. We can go with this. Let's just stick with this lead and the Asian ozone thing. Just I wanted to give you the mechanics. We've probed the mechanics quite deeply with the aircraft by flying back and forth around Fresno in the San Joaquin Valley and measuring what the mixing is in this boundary layer, which I unfortunately can't take the time to really explain to you, but Shane is an expert, so he can tell you about it. But this mixing at the top is a key parameter that we don't normally observe on the ground. Well, Shane might argue about that if you get a good LiDAR. But in my opinion, the aircraft is great because you can sample that region and you can tell what this mixing rate is. And the thing about this San Joaquin Valley, and not too dissimilar here, is that this is about on average a kilometer high, the Coast Range. If you think about this continuing to the Tehachapi Mountains in the south, the transverse range, that average is about 2 kilometers, and then the southern Sierras are about 3 kilometers. So you have this sort of twisted bowl with a rising rim around the south and up. And so this air has a really interesting trajectory as it slams into that and pools up, and the heating along the sidewalls of these mountains actually vents a lot of the polluted air up into this intermediate layer. Oh, I'm going to show you this. This is fun. So I'm not going to focus on that mixing, which I want to tell, maybe I'll just tell Shane or one-on-one. It's a little bit technical, and I'm doing way too many things here. But this is, NASA has this Alpha jet. It's an old German fighter training jet that these rich Google dudes bought and wanted to park it at the NASA hangar. And they said, yeah, you can park it there if you give us a pod that we can fill with instruments and you can fly around where we tell you to and make measurements of the atmosphere. That is what's called Ajax, and this is one of the scientific aviation planes flying together here. And Ajax does these profiles one of these days during this summer project with the ARB, and they do this dark blue is the Bodega Bay. They do a profile of Bodega Bay. Then they do a profile in Visalia, the heart of the valley. And what you can see is, let's stick to something do you want to do? Methane. Big source in the valley. Dairies, oil production, lots of methane coming out all up and down the San Joaquin Valley. And you can see, relative to offshore, at the coast, of course, yeah, it's elevated into methane. Duh, no big deal. But look how up here, in this one profile, they capture these little lofted blobs of methane. Same thing with CO2, but agriculture is sucking it down in the San Joaquin. So the surface of the San Joaquin is actually a sink of CO2. You see lower CO2 being influenced by the San Joaquin Valley. So, and then also it happens in formaldehyde and ozone, and what you see is this sort of three-tiered system. And I think this is important because typically when we think of boundary layers mixing with air above it, we think of this air as being more or less background air, sort of from far away, relatively clean, but this is air now that the valley's mixing into it that has been partially contaminated. It's got part character boundary layer and part character background free troposphere. Okay, so this is what the data looks like from the San Jose State Group over the course of 3.5 months or so from Bodega Bay, launching these ozone sondes, and you see this goes up to 10 kilometers. So you see the structure, the fine structure, day to day is quite impressive. So this is one of the results from this ARB project that's coming out. They have the ozone LiDAR in the San Joaquin Valley in nearby Celia. And if you look at, let's just look at this one. These are colored, so this is more ozone here. This is a boundary layer depth, this black line. So this is that mixing layer. As the surface heats up, it mixes more and it grows deeper. And what you see is the ozone growing in the daytime down here in this boundary layer, but there's also this lofted ozone that we see when it's not photochemically produced, but it's been lofted up the sidewalls of these mountains. So there's this interesting character that we're beginning to quantify and measure carefully in that what I'm calling a buffer layer, a layer that's part boundary layer, polluted boundary layer, part free troposphere, up above troposphere. All right, so I'm not going to do any of that. So let me just try to link all this together really quickly. This is the concluding idea. So we're understanding that air flowing in over the Coast Range we're measuring it at that site. It blows over the San Joaquin Valley and it stagnates there and gets mixed down to the surface. Now we've quantitatively measured that mixing rate. This aircraft campaign, you're just going to have to believe me. So we measure that. So now we look at the average profiles. This blue one is from the Choose Ridge, the mountain monitoring site. I said, remember, it dips in ozone because there's no precursors there to make ozone. And it turns out ozone is very gradually destroyed naturally through sunlight and water in the atmosphere. So, okay, so anyways, this we're tracking and we say this is the air that ultimately winds up over the valley. And then we can measure the production rate. We look at all the different terms that are creating this curve of ozone in the San Joaquin Valley. And we break it down into the components of wind blowing in, mixing vertically, photochemistry happening, and it also reacts to the surface. That's what all these little symbols try to represent. But the point being that in the middle of the day, when the ozone's rising the most, when you have these ozone problems, these alarm bells, when it hits that threshold that happens in the mid-afternoon, then we can say something quantitative about the mixing. And we can say, and now we can say, oh, that mixing is not what it used to be. The ozone aloft is no longer, say, 50 parts per billion. It's now got, whatever, 4 more because of the Asian influence. And so we can apply that to the mixing rate, and we can quantitatively say how much ozone is mixing down to the surface, and we compare it to the other terms that are creating the ozone. And so this is just a way to now compare not just the total amount, but how much is going into producing and changing the ozone. And so we can estimate the local production, and we can measure the time rate of change, and we can then break it down into the components that are doing it. And so what we find, the upshot of all this, is for the first time we're able to observationally constrain what the contribution is in terms of mixing down into the valley from Asian ozone. And it took a lot of work to get there, and thank you for hanging in and following me all the way there. There's plenty of questions. I'm happy to talk about it and discuss it. Email me if you want to keep the conversation going, but it's a really fun, interesting problem that we were able to quantify. What did I say? The bottom line is like 5 to 10% of the ozone, 8% totally of the local production from local emissions is from this long-range transfer. So thanks so much.
I guess those of you who have